Okay, so we're moving on to chapter 10. We're going to be doing part of it. So that's so this chapter is going to be a lot of looking at converting things like alcohols to halides into SN2 type chemistry and using oxygen nucleophiles, things like that. Stuff like that. And so one of the classic reactions, right? Actually, we started talking about this a little bit in chapter 9, was being able to convert alcohols into halides, and you can do that by actually adding acid, right? Stuff like that. So OH is a pretty terrible nucleophile, or excuse me, leaving group. Okay, but the way that you make that a good leaving group is to turn it into what is essentially water. Stuff like that. So the OH is going to grab, it's going to grab the hydrogen, right? So with that, those electrons are going to come over here onto the bromide. So with that, so you have a good leaving group now. So the bromide can come in and displace the water. So you're going to get essentially a substitution of OH for the Br. So this works with HCl, HBr, HI. So that works just fine. So with that, and so if you're doing it under so if you're going to be doing it under SN1 conditions, okay, you have to be careful because remember under SN1 you go through an intermediate, right? So this is going to leaving a carbocation behind, okay. So in the bromide. So with that, and so this flattens out. Okay, so it can attack from this side or this side, and depending on which way it ends up, you're going to end up with a mixture of stereoisomers. Okay, in this case, it's going to be diastereomers, because we already have one set here. Now, the other problem is with this arrangement is that you can also get carbocation shifting. Okay, so if the carbocation is here, when the Br comes in, right before the Br can come in, the hydride can shift over here to get the tertiary carbocation, which is here, which the bromine can then go in and attack. So you have to be careful about carbocation shifting over. Right. So if you want to do this without the possibility of the shifting and stuff like that, you can use these reagents, so things like PBr3, right? So that'll convert an OH into a bromide. PCl3, this OH into Cl. Another one is thionyl-chloride, SOCl2, stuff like that. And so the way these things work is that the lone pairs here will attack and displace one of the bromides, or one of the halides. So CH3. Right, so with that, so PBr2, right, so with that, so the OH, so with that, so plus, so this is what you do, again, you're going to turn this into a really good leaving group, so your bromide could come in and attack and displace this, right, so, and since it's an SN2 reaction, you get inversion of the stereochemistry. So same thing's going to happen here, right, so if this is a wedge, it's going to become a dash, same thing with the thionyl-chloride. Like that. So these are pretty good reactions. You don't have to worry about the carbocation shifting around. So there is a couple of caveats here. So with that, and so you can't do this reaction with a phenol, nor can you do it with a tertiary alcohol because it involves an SN2 reaction to displace the leaving group with your halide, right? So with that, in order to do that, remember you need a backside attack. So in order to do that, you'd have to actually get inside the ring, so with that, in order to be able to push that away, and also with tertiary alcohols, right? So with that, it's too sterically bulky to do the to do the SN2 reaction. Okay, so you can get some selectivity here. So with that, and so with here, right? So predict the products. Okay, so well, here's an OH and here's an OH, but this one is directly off of the benzene is phenol, so this is going to be unreactive. Okay, but this one can be converted into a chlorine. Right, so we can convert that. So OH into Cl. Right. Okay, so there we go. Oh, forget this. So that just remains how it is. Now, one of the things, we're not going to talk very much about this, but we had talked in the before that it's CH next to a C double bond O becomes incredibly acidic. Okay, and so if you have a strong base, so sodium hydroxide, you probably don't even need something quite that strong. If you have a strong base, okay, this can come in, grab this, and move these two electrons in this bond here, and so this can be. This is a way to make a stabilized carbocation. Okay, so that because you can do a resonance structure, right, where these are going here, that's up there. You can get this resonance structure to make the enolate, right? So there's two sets of lone pair, like that. So this helps stabilize the this carbocation here, and that you can go and use and do any sort of nucleophile, right? So, but that's so this sodium hydride is a good base. It's going to grab that, push that there. Right, you're going to end up with that intermediate where the carbanion, right next to C double bond O, and that can come in and iodine. That can come in and displace the iodine to make this. Okay, so this CH3 is that CH3 there. Okay, same thing happens here, right? You can rip off one of these hydrogens, right, to make. Okay, then that can come in, displace the bromide, right? So there we go. So that, so plus B or minus. Again, plus I minus. So this is a nice way of making carbon nucleophiles. So, okay. So again, you're going to be ripping this away, right? So that you can make the enolate ion. You can do the resonance structure, but the carbanion here is going to attack where the leaving group is to attach the new group. Now another thing that you can do, right? So this is the classic Williamson ether synthesis. So you have an oxygen nucleophile coming in and attacking and displacing a leaving group, and so you make an ether here. Okay, so there's a negative charge here. There's a negative charge there. The sodium and the potassium are just there for charge balance. Okay, and so this is going to attack that carbon, kick this away. That's going to attack that carbon, kick that away. Stuff like that, and so you make yourself a nice ether bond. Works pretty well, but it works through an SN2 mechanism. Okay, so it has all the caveats of any other SN2, right? So you need a good nucleophile, you need a good leaving group. This needs to be small, right? So primary or secondary, right? So this group here, the carbon that has your leaving group, stuff like that. And so the question becomes. So if you're going to make MTBE, methyl 2-butyl ether, some of that used to be used as a gasoline additive before we started putting ethanol to oxygenate it to help it burn a little cleaner, stuff like that. And so your nucleophile could either be this methoxide, and then you can come in and attack here and displace that, or you can have the T-butoxide here come in and attack the methyl and displace it this way. So you could either form this bond, or you can form that bond here. And so since you're taking in, and since it's an SN2, you want that nucleophile to be on as small a sort of group as possible, right? So this is tertiary, right? But this is just a methyl. It's less than a primary. So this is going to be the preferred route. Okay, so your nucleophile can come in and attack something very small to displace it. Okay, so most ethers are fairly unreactive. The exception being the epoxides. Okay, so like that. So they're also called oxiranes. I'm starting to see oxiranes more often, but they are called epoxides. Okay, so like that. And so what happens is it is an ether. But there's a significant amount of ring strain, and by doing a nucleophilic attack, okay, so it's attack here, right, because these are polar covalent bonds, okay, stuff like that. So it's going to hit here and there. You're going to eventually, end up protonating this in the workup to get this. Okay, so you can either do it under acidic, neutral, or basic conditions. And again, you're going to have that attack there, push those up, stuff like that. And so again, it's going to be a just a nice SN2 reaction to get this, and then during the workup, stuff like that. So this gets protonated. Okay. So here we go. Right, so with that, so we have this. So remember, this is where you have a carbon-metal bond that ends up being a carbanion. Okay, so that's going to be your nucleophile. So that's going to attack on this side. Now the reason why it attacks on this side is because of sterics. Okay, and so it's going to push that up. All right, so with that, and then after the workup, okay, so OH. Okay, and then we're going to, so these two electrons become this new bond. Right, so these four carbons are here, right? Okay, the black part is here, so this is our product. Okay, so how do you make with that? And so we talked about a little bit about making alkenes before, right? So it's just an E2 mechanism, okay? And so if you want to do it on this side, you probably would want a bulky base if you want to get it here, because it's the anti-Zaitsev product. But work with me, stuff like that. And so if you have a base in here, right, you're gonna grab this. This is gonna collapse down and kick this away to make that right there. Okay. Now, if you want to do an alkyne, you just do the same thing. You just do it twice. Okay. So again, you're gonna grab one of these, collapse down, and kick this away to make this intermediate. Stuff like that, and then you just do it again where that's going to grab that, collapse down, kick that away. So you end up with the alkyne. Okay, so this H is just this H here. So you just do it twice, stuff like that. And so if you're looking at here, right, so you're going to make, right, so you have an excess of base. You're going to make so notice here, you had one leaving group, so you're going to add one pi bond. Here we're going to have two leaving groups, so we're going to make two pi bonds. Okay, and it's going to happen between them, right? So two leaving groups here, so that means we're going to make two pi bonds, and it's going to end up making them between here, right? So you end up with that plus Br minus. There you go.